Okay, good morning. I'm going to talk about Microworlds for Industry 4.0. This is, I will explain you our experience using Snap in postgraduate courses and master degree of Industry 4.0. The IoT OT convergence challenge that was identified in 2007 and is still a hot topic. This year in Hanover Mess was one of the most hot and controversial topics. Here is a metaphor that we use. The IT mentality, the IT mindset, not the systems guys, it's the developers, people. It's like a skater. So they go up and down many times, and they iterate at high speed and at low risk. So they can fall, but it's difficult to get injured severely. On the other hand, we have another point of view, another mindset. There is the OT, it's like an escalator, and here is the reverse. Here a mistake can be fatal. So the most important is to not make mistakes. So the speed is not the same. It's not so iterative. But in an abstract view, they are doing very similar things. They are going up in a vertical ascension. The notion of digital twin can solve this problem because at the end, the limit, the border, the frontier is safety. So digital twin can permit transfer knowledge, can experiment without safety risks. So what's new is that it's possible to think in a skater way, developing solutions in the digital world, and then when you go to the physical world, you translate this digital implementation to the physical one. There is a standard called RAMI that explains, this stands for Reference Architecture Model Industry 4.0, is a standard IEC 63088, that they define this symbology. That means it's the idea of the Industry 4.0 component. And it's a way to explain the OT guys the notion of digitalization. There is an administration shell. This administration shell is a digital interface. What we do is use a Snap. The administration shell can be implemented in any digital technology, but in particular case, we can use a Snap and any protocol, communication protocol such as HTTP or MQTT that are available into Snap. Go ahead. Okay, here. What we have seen is many engineers have forgotten programming and are afraid of it when they want to enroll to the postgraduate and the master degrees. This is our experience, no? And they forgot these skills, this knowledge in the same way they forgot differential calculus, linear algebra, and so on that they studied years before. We use Python in the first release. We used Python at the beginning, and later we switched to a Snap because our hypothesis. We did initially the hypothesis that every engineer can use Python fluently without problems, and we saw that is not the fact. And we had in the first release, the half of the students had a lot of problems with Python because we didn't want to teach Python. We want to teach the concepts of Industry 4.0, agent, synchronous, asynchronous communications, architecture, concepts, and examples. But for the half of the students, Python was a barrier and was very difficult. So in the next edition, we used Snap, and the complaint was reduced to 0. No complaints, and everybody could follow the course. But here we have a first example to show the method. Let me select. Here is no. I have a problem because if I click PDF, because there is the Sorry, I think I have to be able to copy. Maybe because it's maximized. Let me. Right. I test before. Wow. Oh. Double click. No. Goodness. I think I will have the link here in text. Is open in meta. This one. Okay. Okay, in this example, this is an extension that what I presented last year in a lightning talk using 3D elements, and this is improved. So here we have an open 3D viewer, and the viewer opens here. And then what we can do here is we can, in a similar way that last year, we can show the axis. We can, for instance, create a cube. We can create a cylinder. And here we have operations of CSV operations, add, subtract, intersect. We can subtract. But here we have three elements. If we introspect, we see that we have two cylinders and one cube. So if I remove, and I only keep the last one, I have the object with the subtraction. So we can also apply textures, and with texture we can have different materials, so it's a better look. This is the first step. So the second example is a little bit more complex. And so I open viewer, is clean the viewer. I go to houses. Okay, I can build a house. And house is an element, it has been built. And here is a very simple house. We have a door. This door has been built using a subtraction. Here is a fake window because it's a photograph that is like a texture. And okay, and we can move. I have to improve the moving, but we can go, enter, and well, what we can do now is create another house. So I go ahead. We can create another house using this block, and with the block pose, I can move, rotate, and make and put wherever I want the other one. So I can clone the objects many times as I want, and even I can try to automate. So if I clean again and I execute, and I put a ground, I put sky, and I have the floor that is not shifted, so I can fix it with this pose. So we can create in more or less realistic way different concepts. What is interesting here is the same concept of the last year. We have absolute coordinates, we have relative coordinates, we can define containers, and each element has its own container, so we can build a composite complex structures. And what we tell to the students is the method to learn is deconstruct. In order to understand this, is deconstruct the example. For instance, I go here to steps, I have a clean, and if I go, you have category cities, and I have a primitive, house, front wall, lateral wall, window, ground, so on. So, for instance, the front wall. The front wall creates this shape, okay? And if we want to see what it does, I can edit. And what we tell them is, please it's like a debug, but a manual debug, no? You put here, and then what we can do is to execute the instructions step by step. So I will go here, and let me do 4 or 3 or 4, or no more. So you can, in order to understand how it works. So I clean, so I create the parallelepiped, so the first one. So this is a square. And I pose it, well, I rotate it because I create another parallelepiped, and I pose, so I have the 2 shapes. And what I can do is subtract. It happened the same we have seen before, so I have to remove the 2 pieces I don't want, and here I have a triangle. So, and then I can continue composing. Let me show you. I think it's better see the whole. So I create the other parallelepiped. I make a union. I remove the 2 that I don't want. I post it. I create a new parallelepiped to make it, to make the door. I make a subtraction. Here is a parameter. Okay, so I invent it, XXX, and here XXX. I remove. Okay, and I have the door. So this is the way to create, and students, okay, you execute step by step and you learn. Yes, in the background, what they have learned theoretically is a composite. So for instance, we can apply a transparency, and the transparency is applied to all elements in the composite because we are applying the composite pattern. So there are notions of computing, but they don't know, they don't need to know these concepts to apply it. Okay, second example. The second example is we have a model. No. This again, let me. It's a disaster. I don't. Why it happened? No, but I don't understand. Let me go. I open the PowerPoint better. Disaster. Snap-on, DPTX. Sorry. Okay, sample 2. Here. Yes, this is the typical example of continuous control. It's an inverted pendulum. We have an equations, and there are many ways. Euler method is one of the simplest way to solve it. If you substitute this equation with the terms of the derivatives of the Euler method, we have an expression. This is an algebraic expression that I can use and put in my modeling snap. So we think that, we believe that, okay, you can understand or not understand, but you have the equation. What we are going to do now is we go to this example, and this example is example in Snap. I'm in a hurry now. Well, here in this green block, this is the question. It's an if-like equation. This is a loop, and the other method, we execute step by step. So if I run this model, what I have is, here. It's a pendulum. If I make here an impact, this is a pendulum. It's not at real speed, but is executing this equation. Okay, good. But one of the concepts that we have IT students and OT students. The IT students learn IT concepts with Snap, but the OT students, we try to help him to understand OT processes. And this is an example of OT processes. For instance, an inverted pendulum. So this is the concept of PLC. The PLC, this is a typical industrial element, is a super loop. We can see this code of the super loop, and it's very simple in code. I don't have no time to explain, but here there is the correction of proportional, derivative, and integrative. So there are simple algebraic equations. How does it work? If I make a perturbation here, it is instability. Here is the correction. So this is the behavior of the inverted pendulum. So I can fix, look that there are some oscillation. If I fix well the parameters, as I do in this block, here the behavior is much better. Okay, so this is a microwall of control using an inverted pendulum. But we can mix what we have done before, the representation of this inverted pendulum using the 3D viewer, the representation. So here we open and we have the pendulum in 3D. So if I execute here, the perturbation, so reverse, no? Okay. Here I can visualize at the same time the animation in the 3D representation using the same primitives you have seen before. So we have microworlds with the standard snap representation, and we have the microworlds with a 3D representation, and we can make some realistic, okay, 2 minutes, wow. I have to go very, very fast. Learning curve in Snap is short, but it's not immediate. That means that for students, this approach is okay, but in the engineering association, time is shorter. So when we show a microworld into Snap, the Snap offers many, many distractions because many, many menus that they understand. So what we can do, what we do is put into microwall, maybe the wall, we use the term view of microwall because I know that there is a debate and a discussion about if microwall must show or hide elements. And here we have the same model we have into the form that was presented in February that let us, so it's the same code, the same example. If I go here to the house and I execute the house, I have the same example that we have seen before. So here it looks like this is more integrated, but in fact it's an iframe. So it is. What is interesting in that approach is we can control what we want to show. So 1 minute, the last part of the example. This is the notion of sequence of microwall views. Because what happened? When we want to introduce computational thinking to veteran engineers, we say, okay, this is the minimum viable microwall. 2 blocks, on, off. Which is the part that you don't understand? They can't say, I don't understand. So what we can do is start and stop. And we can explain him, okay, you can drag the blocks, start and stop and use it. Oh, nice. That's okay. You make click. So they learn how to use this. Okay, do you want next step? Okay, next level. The next level introduces, okay, thank you. Introduces start, stop, and you can set the speed. So you can start and you can set a value of the speed. For instance, I can say 4, and I may click and it accelerates. I introduce the notion of reporter. You can see which is the value. Or even if I don't want to deal with parameters, I can increment or decrement the speed. Okay, this is the second level of the microworld. You understand? Okay, next level. And the next level is the same, but they are introducing more elements. For instance, the notion of loop, repeat. So we can use these loops, these concepts. So the idea is to have a sequence of gradual incremental, in incremental way, the microworlds to measure, to detect which are the points that make difficult to understand the computational thinking. Let me show you without executing. The third level introduces more blocks, for instance, arithmetic operations, and so on. The fourth level, we introduce the notion of all the algorithmic structures, and we introduce the notion of variable. And the last level, we introduce the possibility to act as an agent using MQTT and connect different microworlds between them. The last slide, recap. This is the end one. According to the general framework of in industry, that is ISA 95, systems can be discrete, continuous, or batch. For discrete systems, we presented in 21 the SDL for Snap is using SDL for automatas and discrete systems. For continuous systems is that we have seen today with differential equations and so on. And the last one is the microworlds can connect to external systems using, such as digital twins, using protocols such as MQTT or ICT. And that's all.
Thank you so much. Please feel free to continue the conversation on the discussion forums. We'll take a break right now and we'll regroup at the top of the hour.